Excellent. All right, so let's get started. First off, Travis was being a little bit generous in his characterization of my involvement here. I certainly was there in the beginning, but Finagle is a product of the effort of very, very many people. At this point, I think I'm more of a sort of spiritual figure than anything else. Thank you guys all for coming here today. It's kind of exhilarating to see that Finagle is being used in so many different ways, and I'm very much looking forward to seeing the talks today and get some more details about that. And thanks again to Travis and Chris and everybody else who helped organize the conference. Despite the little hiccup we had, I think it'll be smooth sailing from here. So we have now been using Finagle in production for nearly 4 years. The code base is actually almost 6 years old at this point in time. Nick made the first commit. And over those 4 years, we've had sort of the opportunity to learn a lot from what it means to run and maintain an RPC system in a service-oriented architecture. And interestingly, just a little bit of trivia, the first production use of Finagle was actually a Java application, which was Twitter's web crawler, the first one we had, I think. And this was a very interesting Java code. Raghavendra, who did this work, who's now at Pinterest, sort of took the model to heart. And there's a lot of Java code with a lot of flat maps and all sorts of different things. But it worked out really well. And so it's kind of interesting to see that the sort of Java aspect of, or multi-language aspect of Finagle took hold very early on. So the other interesting thing is that while Finagle, of course, today is at the core of basically every service at Twitter, the open source community, i.e. you guys and others, has really extended our reach beyond what we could have imagined to do by ourselves. And I think this conference is really a testament to that. It's really interesting and exhilarating, again, to see it being used in different settings. So the sort of core model of Finagle has really remained very constant. I think by October 2010, features and filters and services were all there, and they remain today really to form the kind of orthogonal basis for programming with the system with Finagle. And I think it's interesting to sort of examine why it has endured the way it has. And I think that really boils down to 3 different things. So one is simplicity, the second one is composability, and the third being separation of good separation of concerns. So first of all of the abstractions that Finagle offers is really something that's been reduced to its very essence. A future is really, I think, just about the simplest way you can understand a sort of concurrent computation. And a service is really not much more than a function that returns a future. And filters are really not much more than a standard way of decorating those functions with different behavior. And the result of that is that it's almost always kind of obvious where functionality belongs. There are ready answers and clear answers to what belongs where. And I think that's evidence for this being kind of an orthogonal basis of this kind of computation. The other really, really important thing is that all of these data structures compose in very important and interesting ways. So first of all, as we all know, futures compose with other futures either concurrently or serially to form sort of complex data flow graphs that are very simple to express and have very good and predictable behavior. And services and filters also combine in different ways, very much like functions do. You can stack them, you can pipeline them, and so on and so forth. And the sort of key part of that, of composite compositionality, is that it lets us build fairly complicated structures from very simple parts. And that has a lot of advantages. We can reason about these individual parts in isolation. We can test them, we can develop them, we can reuse them elsewhere, right? And this has turned out to be a very, very important property of this way of programming. And finally, and I think this is a really, really important thing, and I think without this, you couldn't have the others, which is that I believe most of the abstractions in Finagle itself promote really good separation of concerns. And so if you look at something like futures, for example, we're kind of decoupling how code is structured from the sort of concurrent aspects of computation. And what that means is that you're sort of encouraged to structure your computation as effectively a data flow graph. And that allows us to kind of divorce the semantics of computation with all the minutiae and details of spinning up threads to deal with concurrency and so on and so forth. And it gives the underlying system, i.e. Finagle and Twitter util, a great deal of freedom to do interesting things with scheduling those things, for example, or otherwise. And I think it's kind of interesting that now, and I think another important thing about this, by the way, is that I don't think it would be possible to have the kind of compositionality of services and filters without also having futures to kind of decouple the concerns of concurrency from semantics. And so in some ways, they're very much tied together. And I think at this point, in sort of 2020 hindsight, this design is almost inevitable, right? It's hard to find a sort of simpler decomposition of this kind of problem, I believe. If you have found one, please let me know. But I certainly haven't. I think that's kind of an important aspect of this as well. And so I think this model has held up really, really well. So now for sort of the bad news, I guess, which is the following. So I just presented to you very briefly this kind of beautiful Platonic ideal of how you structure these systems together and glue them together and so on. But this quickly breaks down in practice. So I'll call this kind of style of programming your server as a function simply because I published a paper with that name, and it kind of adopted it as the sort of umbrella name for this kind of style of programming. So again, what I just described to you sounds very, very simple in theory, and in fact, most code using this style of programming is very, very simple. But when you start to deploy Finagle in particular, you quickly run into some limitations. And the sort of most egregious of which is that in order to use Finagle successfully today, you more or less have to be an expert at its internals, right? And so we don't have a really good way of separating the kind of semantics that we really need from how the internals are implemented. And I think I'd like to illustrate this with using two different examples. So the first one being that of creating resilient systems. So I really like this definition of resilience, by the way, which is actually from a book about structural engineering. And structural engineering kind of emphasizes this notion of strain. And so I kind of adapted this to software systems as, well, resilient software is software that's able to withstand strain in the form of failure, overload, and varying operating conditions, i.e. Programming in a modern environment. And the reason why resilience is such an important property today is that we're really truly operating with the crappiest computers of all time, which is our data centers, right? And our data centers are really, really heinously complex, and that in and of itself is clearly the enemy of robustness. But they're also really unreliable and prone to operator error. However, they're the only computers we know how to build cheaply and at scale, and so we're kind of stuck with them. And so it's up to us to compensate for the robustness that we forfeited in hardware in our software instead. And the interesting thing about resilience as a property is that it's really a systems property. It's not enough that a single piece of software in and of itself has some modicum of resilience. It's really the system that has to be resilient, because that's what matters at the end of the day. It doesn't matter if your little service performed beautifully while the whole site was melting down, right? And in particular, this kind of requires the adoption of a kind of systems thinking to solve in an acceptable way. So why is this important for Finagle? Well, Finagle kind of has an exalted position here because I like to say that it occupies the boundary between independently failing servers or mutually hostile states or whatever. Like Finagle is that buffer, basically. And Finagle provides a lot of the important tools that you can use to create resilient systems. And so these are things like timeouts, failure detection, load balancing, queuing policies, and so on and so forth. Now the trick here is that in order to create a truly resilient system using Finagle, you have to piece all of these things together just so, right? Like you have to understand how they all fit together, how they all interact, how to parameterize them in order to successfully use Finagle to create a resilient system. So just to walk through a bit of an example, you can imagine that if you have a system today, first of all, you have to tune its timeouts, both on the server side as well as the client side. You might use client timeouts in order to sort of maximize your chances of success while also not getting bogged down by slower and unresponsive servers. And so here already we see kind of contending needs. We have kind of service level agreements needs as well as liveness needs, right? And we use timeouts as a tool to address both of those. And at the same time, you want to make sure that when you do encounter a failing or a slow server, that you have room to retry those operations where you can, right? And so already we see that a simple seeming knob like timeouts, a configuration like timeouts, already deals with a lot of contending needs. The same is true of tuning retries. So you want to make sure that your retries are set so that you have basically a good chance of retrying failed operations when they do. But at the same time, you don't want to effectively denial of service attack yourself by effectively getting into traffic amplification or something like that, which can occur with retries as well. This very much shows up in things like connection pools and queue sizes. You want to make sure that your inbound queue sizes are not so large that you won't just infinitely accept work that you're unable to perform, but not so small that you limit the throughput of your service, right? And what we end up doing in practice to tune all these different things is basically to load test them using tools like Iago, for example, which is another open source product from Twitter that allows you to generate traffic. It was kind of designed for this purpose. And from your sort of rough estimation of how your system behaves under these load tests, you more or less pick out of a hat, what your parameters are and kind of hope for the best. And I don't think that's necessarily a sustainable strategy. And finally, also another really important thing, another important tool that Finagle gets you in order to create, so that you can create resilient systems, is the ability to do kind of failure classification and handling. So if you have a system, you need to know whether or not you can safely retry a particular failure, for example. Right? So this is not really to knock on this method. In fact, we have many, many remarkably resilient systems created in just this way. And in fact, Twitter today is full of them. And I believe that at this point in time, the sort of Twitter infrastructure is a fairly resilient one. And this is how we accomplished it, right? But it's a lot of work to do, and also a lot of upkeep. Your operating environment changes constantly. You might have new clients that talk to you. You might have to talk to new servers. Maybe you enter a new data center, which has a slightly different network topology and different latency profiles and things like that. And in order to really maintain this kind of resiliency along the way, you really have to remain vigilant. And it's a lot of manual labor and a lot of just sort of upkeep and load testing and doing sort of implementing good software development practices in order to create a truly resilient system. Now, another sort of important aspect of the way Finagle is tuned today with all these different parameters or the tools that you have available to you is that they're all intertwined. And I hinted a little bit at this earlier where timeouts, for example, are used for lots of different purposes. But the same is true between parameters as well. So, for example, maybe you want to, maybe you want to increase the amount of concurrency that your request concurrency in your server. Doing so almost invariably has sort of downstream effects on all the other parameterization that you have, because you tuned your system to handle a particular level of concurrency, and now you changed that for whatever reason. You have to sort of reconsider everything else that you do. So that's one problem with this style of system, I believe. And we do have an answer for it, but it's not a very satisfying one, right? It's clearly kind of a breakdown of this model. We have this sort of really clean and orthogonal model to work with actual application code, but in practice, we have to do a lot to make it work in the kind of setting that we want to. Another really big problem using systems like this, and by this I mean sort of service-oriented architectures, is that you forfeit basically all the flexibility you have in more monolithic applications. And so this is a very rough, not representative, cleaned up outline of sort of how Twitter, the Twitter infrastructure stack looks like. And so on your left here, we have the front-end web servers, which fronts a bunch of front ends, basically HTTP front ends, which talk to some middle tier of effectively domain logic and servers, which then talks to a storage layer. So if you imagine, all this logic is now spread out all over the place and executing independently all over your data center, whereas before you had it all under one code base. And in the process of doing that, you forfeit a lot of the flexibility you had in the monolithic code base. So for example, consider just production testing a new service. So maybe you have a new version of the user service that you want to make sure it doesn't break in practice. So the way you would do it on a monolithic application is that, well, you check out your Git branch or whatever, and you make the modification, and you maybe deploy it to a few servers, and that's it. Right? It's all under the same code base, and so you can do that very easily. In a service architecture, everything is much more complicated. So in order to do that, you would have to deploy a few instances of the particular service that you want to test and roll out. And not only that, but in order to actually understand how it behaves under whatever load you want to give it, you would have to orchestrate every service above it to sort of reroute or redirect traffic to that particular service. And that's just one very simple example of how distribution complicates things. There are numerous others. And I think it's pretty well recognized that when you distribute your application, you forfeit a lot of the sort of simplicity of working with this code base in practice. And again, this is this kind of the monolith versus service-oriented architecture discussion. And this, by the way, extends not only to things like testing a particular service, but imagine all the different tools you have available to you in a monolithic application. First of all, you can sort of printf anywhere you like, right? That's actually a useful, really, really useful thing to do. Well, in a service architecture, you can't really do that. In order to do that, you would have to add your printf to a service, deploy it someplace, hope that the right traffic lands there, and look at its logs or something. But it becomes very, very difficult. The kind of impression I'm trying to give is that basically everything becomes more difficult in this kind of setting. And printf is just one of the examples. There's things like debuggers, dtrace, a lot of these different things that you kind of forfeit. So maybe it's worthwhile to think of how you might account for these kinds of deficits effectively in an RPC system. So far, both in this talk and in Finagle generally, we've been kind of operating with a very simple model of what RPC means. Namely, that the role of an RPC system is roughly just to link up two different components and figure out how to dispatch a function remotely. That's more or less it, right? And everything else in between, of course, is a lot of complicated stuff that happens. But that's the kind of model that we're kind of adapting. And you can kind of reduce that to say, well, Finagle's role is to either export a service implementation from a server or else import a service implementation from some other servers, right? That's roughly what the role that Finagle plays, right? And that kind of assumes this very simple model. And again, of course, Finagle does a lot to accomplish that. There's everything from load balancing, connection pooling, liveness checking, and everything like that. And I guess one other thing that deserves mention is that the model of Finagle is actually one of kind of replica sets, and so it's not just a single instance. It's a pool of identical instances that you're dispatching to. But that distinction is not super important for the purposes of this talk. So in many ways, that model is really the least we can get away with from an RPC, from kind of an RPC perspective, and it is the sort of traditional interpretation of what RPC means. But it also doesn't solve these kinds of problems that I've outlined, right? In fact, it's complicit in creating them, right? Because it's the thing that allows us to distribute stuff, and now we have distribution, and now our world is painful, basically. And so I think it's worth thinking about how we might sort of account for these sorts of things in this model. So first of all, I think it's also important to address the question why would we need to tackle this in an RPC layer in the first place? there are lots of other different ways of accounting for these kinds of problems. So for example, maybe you introduce software load balancers that can route traffic in particular specialized ways that allow you a great deal of flexibility in how that's done. Or maybe you have specialized front ends that allow you to stage certain servers and make use of them and easily kind of integrate yourself into that kind of development cycle. I think that approach is very traditional and it's being used successfully, but I also think it's has several problems. First of all, they're all very narrow in scope, right? And so I might deploy a sort of staging system that is specialized for my particular infrastructure for maybe front-end web traffic, and that's it. If I need to do something that's outside the scope of what that is intended for, I'm out of luck. Another thing is that these kinds of infrastructures tend to operate below the session layer in the kind of OSI model. And what that means is that they don't have access to a lot of the kind of semantic goodness that you want to do a lot of smart things. So for example, I don't have access to what my framing looks like, or what the timeout for a given request is, or whether or not a request is retriable or not, right? Because I'm just dealing with byte streams basically most of the time. And then finally, they also just constitute more infrastructure. You add more infrastructure to solve more problems, but there's also more complexity and more things that can fail and so on and so forth. And so I think it's worthwhile thinking about how we might instead account for these kinds of problems in the RPC system itself. So the way I've been thinking about it is that I think it breaks down into three main components, which is one, to have a component model, and I'll get into what these mean in just a second. So one is to have what I'll call a component model. The second is what I'll call a linker, and then finally an interaction model. This is actually a kind of model that we've been working to move Finagle towards, and you'll see shortly how that plays out. But first I'll explain myself. So what do I mean by component model? Well, it's basically your server as a function in this case. It's kind of how you structure components and how they fit together, and how you how they compose and so on and so forth. And I think Finagle's basically works. And again, I think it stood the test of time in many different ways. There is one sort of common deficit, however, which is it's very difficult to interpret failures from Finagle. And so a future can carry any throwable, and a throwable in and of itself doesn't mean very much, right? So as a simple example, if I see a failure from a Finagle service, I don't know whether it's safe to retry it, without knowing more about the actual implementation. And again, it's about sort of coupling, or we're trying to decouple the implementation from the semantics of the API. And so toward that end, we recently introduced a failure class which kind of bridges that gap, which is a failure is also a kind of throwable, but it has sort of semantic provisions for telling what an error is actually about and what you can do with it, right? And so in particular, it has a set of flags, and these flags allow you to represent things like, well, this failure is retriable, or this failure happened because the operation was interrupted, or so on and so forth. And because we now have a common way of talking about the semantics of a failure, we can suddenly do more general things. So as an example, you could have a retry filter that just tests whether or not the failure is retriable and just blindly retries any retriable failure. And again, this helps us to sort of decouple the semantics of a failure from the underlying implementation. And so that's really a small modification that we've done, but I think actually one that is very important. And that's really, I think, all the changes that we have made to the sort of core component model here. And now I think for a more exciting part. So usually, the way Finagle clients are constructed is that you give it either a static host list, so this set of hosts, or else maybe you use the server set. So server set is implementation effectively a dynamic host list using Zookeeper, right? And I know many use that. We use that at Twitter very heavily. Server sets are really, really useful. they allow you to maintain these dynamic host lists that come and go when, as service become available or go away, and Finagle will load balance over, effectively the current snapshot of that host list. But they're also very limited in the sense that they really are just a host list and that's it, right? They're really just a dynamic version of this host list, the static host list that we have talked about. So one thing that we have recently introduced is the ability to do symbolic naming in Finagle instead. And what that means is that instead of using these sort of concrete notions of destinations or targets like host list, static, or dynamic, you instead introduce a purely symbolic version of a destination and then let the environment interpret what that actually is. And I think that's best explained sort of by going bottom up in terms of how it's actually implemented. And I hope to convince you that this is a very powerful and useful mechanism. So first of all, the very lowest level of a destination in Finagle is this thing called an adder. And so an adder is effectively a case class or an ADT that may either be bound. And so bound adder has a set of socket addresses. So these are things we can actually connect to, right? It could be failed because maybe the thing that produces the adder failed. Or it could be negative, which means that that destination doesn't exist. We know that it doesn't exist, right? So that's what an address is. Now, on top of an address, we have something called a name. And so the interesting thing here, by the way, is that addresses are both concrete and static, right? This is just a regular socket address. And addresses describe concrete destinations. If I have an adder.bound, that represents a concrete host list, effectively, that I can connect to. So names are kind of interesting. So names have two variants. One is that it can be bound, right? And the trick here is that a bound name has a variable address, right? So that's an address that can change. But what that tells me is that my name is, so name is something that represents the destination. This tells that the name is actually bound to this variable representation of an address. And the only thing that, for the purpose of this talk at least, that you have to be aware of is that this var effectively denotes that a value of this underlying type can change under you, basically. Now the more interesting thing is this variant called a path. And a path, again, is a symbolic name. Symbolic names are hierarchical. So as an example of a valid path is something like this. Maybe it's the main user service in this case, right? And so we'll take S to mean service, and then user to be the kind, and main to be the particular deployment, I guess, of a particular service. And that has pretty profound effects on how we treat names and naming in Finagle. So another thing that, an important note on top of this is that users of Finagle will rarely encounter names by themselves. Instead, there's a mechanism to effectively parse a string into a name for you. This is called a resolver. And so in Finagle, this is how we write our code basically. You might create a new client that derives its address from, or name rather, from the zookeeper or service that's stored in the zookeeper path. And in this case, this is a name.bound, this is a name.bound, right? But this is a name.path, right? And so here I've instantiated a client that has a destination that is purely symbolic, right? And so now the question is, if I had told you no more, that would be basically a no-op. That's completely meaningless. And so we have to have a way of giving meaning to these kinds of names. And that's a process called interpretation. And so again, interpretation is basically a way of turning a path into a bound. So name.path into name.bound. And the way that's done in Finagle is through something called delegations. And what a delegation is that it's effectively a way of rewriting a path into another path, right? And so here's a particular kind of delegation that says, well, paths that begin with /s get rewritten to have this prefix instead of the /s prefix, right? And so in this case, if I had s user main, it would be rewritten to zk local twitter.com 2181 user main, right? And so it's a simple sort of prefix substitution rewriting rule. And so that is what a delegation is. Now, that's not super interesting by itself, because if all I had was a way of specifying how to rewrite a path into another path, that's still just rewriting in the void. It doesn't give me anything. And so there are special kinds of paths that give rise to special kinds of interpretation. And those we call system paths, and they begin with $. And so, for example, the path $/com Twitter server sets don't result in rewriting, but rather in something called the namer handling that rewrite. And so, for example, in this case, paths that begin with $com Twitter server set take the sort of residual of that path and give it to the server set namer, which then can interpret it. In this case, that namer returns a name.bound that has the actual value of that server set. Now, the interesting thing though, is that namers can terminate, like I just described, by returning a name.bound, but they can also recurse by returning a name.path, right? And so that might say, well, this path is really this other path, and reinterpret it in my current delegation table, or they can return a negative result, which is to say, this path doesn't exist authoritatively. So the way, and I hinted at this just a few minutes ago, so the way sort of everything is tied together is through something called a delegation table. And a delegation table is an ordered list of delegations. And this is what we use to interpret these names in total. So in this particular case, oh, and by the way, rules apply bottom up, so later rules win, basically. So given this delegation table, if we try to interpret our previous name, which was suser main, it would first get rewritten to serve prod user main, which by this rule, then into zk local prod username by this rule, and then finally to $com Twitter server set, and then the rest of that path by this rule. And here it would terminate because that is something that would return a name bound to me. Right? Now, where it gets really interesting is when these namers return negative results. And when they do, Finagle will actually backtrack the interpretation. So imagine you have a delegation table like this. And notice here that there's two definitions for SRV, right? So there's one that goes to ZK local and one that goes to ZK remote. And so by the previous rule, or the previous rule that I described, we'll first try to traverse this path and try to resolve a name given this rule, and we can see how backtracking works here. So again, we try suser main, it gets rewritten into serve prod user main, gets written to ZK local, and then finally into the actual zookeeper concrete namer, which returns a negative result in this case. So maybe that server set doesn't exist. And in that case, we actually backtrack up to this step again, number 2, and try the remote one instead. And in this case, maybe it succeeds. And the net effect of that is that we effectively have kind of overlaid namespaces. So in this case, I can say, well, try the local one, and if that fails, try the remote one. It's very kind of similar to how a union file system might work, where I have several layers, and I traverse those layers in order to find a name that actually results in a service. Now, the interesting thing about that is that we now have a way of sort of separating symbolic names from how they're interpreted, right? And so I might in my code just talk about /suser main, but I might alter its environment by modifying the delegation table, right? And not only that, but the delegation table gives me a lot of interesting flexibility, which I'll get into now. Right, and so again, what this ends up being is that we effectively have a sense of location transparency, where I'm just talking about these symbolic names, and the actual concrete location of what those names refer to is transparent to the client. And some simple examples of where you can use that is, for example, well, imagine that you have several different environments that you're deploying your processes in, your servers in. You can, without changing the code, just alter the meaning of those names. So perhaps in a staging deployment, you want to talk to other staging servers. Or perhaps in development, you want to talk to only servers that run on your local laptop. We can now affect these kinds of interpretations without changing any configuration at all, just by changing the delegation table itself. So the delegation table, in some ways, encodes your operating environment. So The interesting thing, though, is that we took this idea much further, which is when you think about what it means to be an environment, you might think, well, maybe it's a process lifetime or something like that. That's kind of the logical delimitation of what you might consider. Instead, these delegation tables, these environments actually apply on a per request basis. Right? And so what that means is that I can actually have a different delegation table for each individual request. And that allows for some really, really interesting things. And not only that, but those environments can escape your particular instance into service that you're talking to. And so we have support in our RPC protocols, so MUX and HTTP in particular, to ship effectively delegation tables across the wire. And so if I operate in a particular environment, so will the systems that I'm calling, right? And so, for example, if I'm staging, then the system I'm calling will also just inherit the stagingness of my environment, and it will dynamically reinterpret its names for the purposes of that single request to those of the staging environment. Right. And that turns out to be really, really interesting. Right. So here's that example concretely. So perhaps I want to deploy. So this is kind of the example that I give initially. Maybe I want to deploy a new version of a user service that is staged, and I want to send a traffic to see how it works. Now I can simply issue a request from my very front end and say, well, this request, or request tree, should operate with this amended delegation table, this amended environment. I'm modifying the environment of the whole request tree. And no matter where that request goes, /s/user/main will always be interpreted now as /s/user.staged and not the original definition. And that shows one simple way in which this thing is very powerful. And in fact, this is how we now do staging at Twitter. And so we no longer have specialized staging infrastructure. You can simply deploy your system somewhere and instruct our HTTP frontends to amend the environment to account for your staging server. There are a lot of other interesting uses of this technology. First and foremost is the ability to define environments dynamically in the way that I described. But there are many more. So for example, we use this mechanism also to do cross-data center load balancing. And the way you can think about that is that I'm just talking about a symbolic name like /s/user/main. The environment might choose to say, well, what it means to be a /s/user/name is to send 80% of your traffic to that data center and 20% of your traffic to that other data center, right? And again, this is completely transparently from the actual client code, right? And another really interesting thing that we did is I think in January, there was a hack week at Twitter that we have occasionally. And Oliver was sitting right there, and who's no longer at Twitter. And Antoine, who I think is climbing somewhere, and myself, we got together and just in a matter of a few days, implemented effectively the moral equivalent of D-trays for distributed systems. And what that allowed us to do is basically define a way of matching traffic. So maybe I want to see 10% of traffic that goes to the user service, and given that traffic, I want to run this little script. So maybe that script is to just print it out. So here's my printf, right? Or maybe you do more interesting things like maybe you want to do a chaos monkey-like thing and fail a certain percentage of requests. Or maybe you want to do hypothesis testing about your system as a whole and delay, effectively introduce artificial latency into your request path. And this we could all just do by defining this little dtrace or awk-like scripts to match traffic and then execute a rule. And this is all made possible by the fact that we have this kind of symbolic naming system and are able to interposition systems in between other systems so we can do interesting things like this. This is a quote from an anonymous Twitter engineer who was impressed, I guess, by being able to do this stuff. So, moving on. So the other thing, so we talked about flexibility, so rather we talked about a component model, a linker, and so this is what I call a linker, basically a system responsible for piecing together all the services that we're operating with. And finally, we have the interaction model. And what do I mean by that? Basically all the kind of problems that I outlined in the beginning. So how services interact with each other. Today, basically, Finagle has a lot of this stuff, but it's very weakly defined, or weakly specified at least, right? And so again, Finagle does all this stuff with respect to load balancing and queuing, timeouts, retries, error interpretation, and so on and so forth. But as I hope to have convinced you of earlier, this requires a lot of effort and a lot of kind of tying the implementation details or specifics of Finagle with the services that you're deploying or the code that you're working with. And I think it's possible that if we are able to raise the sort of level of abstraction a little bit, we can do a lot better. So you can sort of think about what are your goals when you're deploying a distributed system or a component in the distributed system. Here are a few that tend to show up over and over again, which is, first of all, your system has to be well conditioned. And what that means is that you want to be able to reject requests when you're overloaded so that you don't slow everybody down, right? So you prefer to reject, say 20% of your requests versus slowing down 100% of your requests. You want to be timely because otherwise, the work that you're doing is useless, right? Like you basically want to respond in a timely manner. Otherwise, your users will leave. And also, you want to be well behaved. You want to be a good citizen in this kind of distributed environment. So, for example, you want to make sure that you can't overwhelm systems that are downstream from you by unintentional or intentional traffic amplification, for example. And kind of as I alluded to earlier, this really requires a lot of vigilant tuning and deep understanding of how Finagle works in practice. And I think that's problematic for lots of different reasons. First of all, again, as I kind of alluded to, there really are a lot of conflict, or we use these tools, so again, tools like timeouts and retries and so on, to serve multiple conflicting goals, right? So for example, you might use timeouts to deal with resource management, basically, because you want to make sure that you don't have really long-lived objects in your heap. You use timeouts to deal with liveness concerns because you want to make sure that you don't succumb to a down server that will never respond. And you also use timeouts to sort of effectively express your SLA, your service level agreement, right? And so that's just one example where you effectively have three sort of separate orthogonal goals all bundled up into this one parameter that you have to supposedly should tune, right? And those kinds of trade-offs show up all the time. So like let's say you went through the exercise of saying maybe this system should tolerate a higher downstream error rate. Well, maybe you can increase the retry budget then. But then you might also increase your concurrency level as a side effect of doing that. Well, then maybe you have to create larger connection pools. But connection pools generally, you size them generally to deal with spikes. And now, because of that, you can now affect the rate of promoted objects and so on and so forth. So there's a really, really large sort of cascading effects. And without sort of understanding what the underlying goal is, right, you're stuck with these sort of low-level knobs. And again, you're sort of stuck tying yourself to a particular implementation and a particular behavior. And that really ties the hands of the implementers of Finagle, right? Like there are a large class or category changes that Finagle just simply can't do because people are effectively assuming a particular behavior from Finagle. Another problematic aspect of this is that this kind of configuration is inherently static in the sense that it fails to respond to varying operating conditions, right? And so you tune this at one point in time, and then 2 weeks later, your operating environment has totally changed, and you fail to account for that in your service, and you effectively lose all the work that you did. But I think, again, like the most troubling fact about this kind of arrangement is that it compromises abstraction and modularity. Finagle is now unable to do a number of things, and we've effectively tied ourselves to a particular implementation. So one way that you might address this is to, instead of talking about all this low-level configuration, instead talking about higher-level goals, right? So the goal effectively expresses the behavior that you want, right? And so I think there are roughly two sort of large categories of goals. One is service-level objectives, which effectively allow you to express what is what is my expectation for an SLA for this request, right? So, for example, you might have a deadline or a timeout to express that. And on the other hand, you also want to make sure that your system remains fair and that it manages the resources efficiently. So you might also have effectively cost objectives. And those might be something like, the amount of effort you're willing into trying to satisfy a particular request. Right? And that sounds like a pretty simple change, right? In the sense that you change the API to explicitly not deal with these low-level configuration knobs, but instead directly with a higher-level goal. But I think the implications of that are quite profound, because now Finagle has the freedom to do whatever it can to meet those goals, and we have a crisp definition of what the actual expectations are, right? And we actually have a way to converse about those kinds of trade-offs and introduce dynamism into the picture. So I think just about the simplest SLO that you can come up with is a deadline, right? And so a deadline is basically, after this time, the request, or the response rather, for a request is no longer needed. Maybe that's because you're unwilling to wait for a certain amount of time, like it's an actual user level goal, right? And so in Finagle, we actually introduced the ability to express that, and we have a simple case class that basically allows you to express what an actual deadline is, and then a standard request context that allows you to set that for the context of your request tree. And just like the delegation tables I described before, these are transmitted across process boundaries using our RPC protocols. So if you set a deadline in one system, it gets transmitted to your downstream systems. And this seemingly simple change actually allows you to do some really interesting things, even up front. So here, for example, is now a very, very simple admissions controller that simply rejects requests that have already expired, right? And so you might think, well, is that really useful? And the answer to that is absolutely yes, because you might, for example, have a server that undergoes garbage collection or has some other hiccup, or there's a network hiccup, for example. And this allows you to reject requests that are not going to, whose responses are anyway useless, and allow you to effectively shun work that is useless, so that you can get yourself up on your own feet, right? And this is, again, is a very, very simple admissions controller, but nevertheless a useful one. And Ruben and Bing, who are in this room as well, are working on more sophisticated controllers that account for actual runtime behavior. So you can imagine treating a service as effectively a black box and trying to estimate how it would respond to a particular request, and then based on that estimation, shed work early, for example. This is similar to how network routers do random early drop and things like that. And even in this simple form, it's very, very useful. And again, this is very much ongoing work, but I think what we're hoping to move towards is expressing these high-level goals and then do simple but quite effective things in the actual stack to both manage those resources as well as implement the SLOs in whatever form they are. Which leaves, how do you express the sort of resource management or cost objective aspect of this? So we talked about how you want to say, here's my SLO effectively, here's my service level objective, but you also have to be able to express how much you're willing to pay to effectively achieve that, right? Because perhaps, and to account for things like making sure that you're a good citizen, for example, and not overwhelm downstream servers. And so one thing that we've done in Finagle recently as well is to introduce this notion of a Fanout Factor. And this is, in essence, a simple version of a cost model. And what it does is it effectively allows you to set the ratio between how many requests are asked of Finagle and how many requests Finagle will actually try to perform, right? And to see why that's useful, you can imagine, well, maybe Finagle needs to perform a retry in order to try to successfully dispatch a request because the first one failed. Well, this effectively gives you a budget for those retries, right? And you don't have to now manually specify here, this client has this static retry budget, this other client has this other static retry budget. And again, that is problematic for all the reasons I described before, where you're fixing this very static thing, but the actual goal is that you want to be a good citizen. Here you can basically say, well, this is what it means to be a good citizen. Finagle, you're free to retry as much as possible as long as you remain within the bounds of this, right? And you can also imagine having more sophistication now, for example, deriving automatic backoffs based on your budget, right? So, and things like that. And the goal is, the idea is very much the same. We have this notion of a high-level goal, which frees the developer from reasoning about how all these different knobs interact and how they should be tuned. And we're instead able to sort of dynamically interpret how to execute on that goal, right? And I think a lot of interesting stuff is going to come with that, though that's largely future work being done by the core services team at Twitter. So I think in conclusion, basically we're moving towards a model where RPCs kind of operate at a higher level of abstraction. And so instead of treating RPC as a simple remote dispatch primitive, we also have introduced this notion of having high-level targets, so symbolic names, service objectives, and cost objectives, and so on. And I think the kind of important thing here is that both of these things allow us to kind of separate the semantics of what you're trying to accomplish from how it's actually being executed. It kind of increases the level of separation of concerns that we have in the stack. And I think that will be very, very useful. First of all, it allows users to express what their goals are directly, and it allows Finagle to do more sophisticated and more interesting things, and more powerful things, actually, because we now have a semantic understanding of what those goals are in order to meet those objectives. And so that's it. Thank you for coming here today, and I hope you will enjoy the rest of the conference. And I think we also have time for some questions. And I'm happy to talk about this or anything else, really. Yeah.
Could you just repeat the question?
Got it.
Yeah, so I have a question about the negative results that trigger backtracking when you're trying a request to a result or a server set. What happens if it fails, if you get a failure type instead of a negative result?
Right, so the question was, whereas if you get a negative result from a namer, you backtrack, what happens if you fail? The answer is that you fail. So the failure propagates, and you don't have a name.
Is there any sort of failure handling strategies you can use on top of this?
Yeah, so the question was, is there any sort of failure handling strategies you can use on top? Not ones that you can express directly in the delegation table, but certainly in code you can. But that's an interesting idea. I mean, you could imagine having an ability to basically say this rule is optional for the intents and purposes of failure.
So doing delegation table, doing the binding part on a per request basis sounds super awesome. I understand all the cool things about that. It seems like it has probably a high CPU cost. And I'm wondering if there's ways to sort of selectively cache and done experimentation. Yeah,
so the question was, it sounds really cool to be able to do per request tree or per request delegation tables. How do you make it perform? The answer is that we make it perform. This works really well, and it uses a fairly sophisticated caching scheme to be able to do that. In fact, the kind of resolution strategy or interpretation that I showed, each intermediate step is actually cached. And so if you reuse different parts from even different delegation tables, we can reuse those results. And so in practice, it ends up working really well. We had a lot of problems initially with that, and in fact, we caused a fairly bad incident at one point in time. But I believe we have not seen any issues at all since then, and it's used very heavily. And so I think we've solved that problem.
Other questions?
Yeah, I have maybe just a sort of a practical question with this. It seems to me that this is obviously, I can see all the power and utility of this, but I also imagine that with great power comes the possibility of great misuse. And I'm just wondering if there's on a practical aspect of this, is there somebody wants to sort of change the delegation table? Is there some kind of review process, or who oversees what these delegation tables look like?
Yeah, so the question is, delegation tables are very, very powerful. How do you in practice sort of deal with the fact that you're giving a very sharp tool and a lot of rope to thousands of engineers? And the answer to that is basically we limit the places where you can introduce delegations into the system. And so in particular, we have modified our front end. So the way that works in practice is that if you're inside the Twitter office and if you're a Twitter employee, you can send extra HTTP headers with HTTP requests, which kind of modifies the route. And we are very careful about the shape of those modifications that can happen, that are allowed to happen. And so we have very strict policies. Now, that's not to say that you can't override that, but you really have to know what you're doing in order to do that. And so that certainly prevents kind of accidental rope hanging, I guess, but without kind of limiting what you can do. So it's kind of like the distinction between ComSun unsafe and whatever else, right? Like we have that backdoor, but by default, we kind of limit the shape of overrides that you're able to do in production, and also the rates of them and things like that, to make sure that we don't accidentally ship a bad Twitter client that has a delegation turned on by default that shouldn't have been there, for example.
So the SLOs that you're talking about, do they compose in the same way that like the lower level filters did with services? Or am I understanding that?
Yeah, so the question is, how do SLOs compose? And the answer is that the way they work in practice is that you set an SLO kind of for some request tree. And so you say, I want this computation to run under this SLO, right? Now, if parts of that computation also set their own SLOs, you pick the most conservative of the two. And so if you look at the implementation of deadline, for example, there's a way of composing it exactly like that, where I say I want to combine these two deadlines, and what is the resulting deadline, right? And you can imagine composing other kinds of SLOs in a similar way. One over there.
Going back to the detail things of the actual cache bars for those things, where on the did you start? Cache separation for negative things.
Yeah, so the question was, how do you deal with cache expiration? The answer is that all of the actual underlying data is stored in Zookeeper in our case, right? So the namer implementation explicitly affords for variability. So you can basically say, the result of this resolution is actually a changeable value, right? So in the case of Zookeeper, we can implement that by having watches and triggering changes based on those. If you're not using that, you could use a TTL. It's up to the implementation. But in practice, what we do at Twitter, at least, is we use Zookeeper for that.
Any other questions? Yes. You talked about having sort of heavily tuned clients and then introducing linking that would allow them to link against lots of different backends that might have lots of different performance characteristics. Do you expect SLOs to fully address kind of the variability there between linked clients, or are there other mechanisms you can use?
Yeah, so the question was basically, when you're a server, you talk to other servers that are sort of invariably variable in their performance. And how do SLOs address that? The answer is that they don't directly address them. And so an SLO just says, here's the objective for my requests, right? And you can inherit that and examine it. You could have a specialized implementation of an admission controller, for example, that accounts for the fact that you know something more about your server than can be known generically. Or perhaps we can come up with good enough sort of black box admission controllers that can account for that, right? So perhaps you can, so as a simple example, perhaps the admission controller can maintain a queue per method, and maybe the variability is kind of contained within the method, right? Or maybe it says, well, the variability of this thing is too great, so I'm just going to throw up my hands and give up, and I'm not going to be able to make a good judgment. But that's kind of TBD, to be honest, yeah.
We have time for one more question.
So do you see GC avoidance being implemented as an SLO?
So the question was, will GC avoidance be implemented as an SLO? So for those who are not familiar, GC avoidance is effectively a feature in Finagle that you can turn on via flag that allows you to route around garbage collections. And so a server can signal to a client, basically, I'm about to undergo garbage collection, stop sending me requests. And the answer is yes, you absolutely can, because now I actually have a way of knowing what the expectation of a request is. And so you could say, well, I expect my garbage collection to last for 50 milliseconds, but my response time is estimated to be 50 milliseconds, and I have a budget of 100 milliseconds. In that case, I don't have to actually reject the request, right? As a simple example. So you can certainly account for it, and it could make things better for sure. In the sense that right now, GC avoidance is an all or nothing proposition. But if it doesn't matter for the purposes of the request that you're serving, then you don't need to worry about it.
Any last questions? Okay, thank you, Marius.
Thank you.